Derivatives is a major goal of this class, and you know we need to look at it through all lenses, and that includes graphically. So that's the point of this video lesson. We're going to take a look at different graphs and how we might graph the derivative function. So here's a graph of a function y equals f of x that's made up of 4 line segments. And the thing to remember as you look at graphing the derivative for this function is here in the box, that the derivative is the slope of the original function. So for example, right here in this first segment, that piece of the function has a slope of 2. So f prime, which is the slope of f, would equal 2 on the interval here from 0 to 1. Now I'd like you to pause the video because I want you to go ahead and take the time to figure out the slopes of the other 3 segments and then come back to me and let's talk about what you found. Okay, so I've done it here. I've got the slopes of the 3 segments, the other 3 segments, so you can compare your answers to mine. I got the slope is 1/3, and then 0, and then -1 on the 3 segments of the graph. So what we're going to do is graph the derivative of this, and the derivative is shown below. So here the y values equal the slope of f, or f prime of x. And so as we look at this first interval between 0 and 1 here, our slope was 2. And so down here on our derivative graph, between 0 and 1, we have a slope of 2. Probably shouldn't have made that little scribble. They're going to think that's the function. Don't get confused by that. Going on. So here, between 1 and 4, on the interval from, oh, I got that backwards, 1 to 4, whoopsie, we have a slope that's much less steep. So it's positive 1/3 there. And that's shown right here. Everything between 1 and 4 had a derivative of 1/3. This constant function, this constant part of our function between 4 and 6 shows a derivative or slope of 0, which is plotted right here. If you look close enough, you can see it there. And then finally our graph finishes in a drop, which means the slope is negative and so is the derivative. The derivative is -1 and we see it plotted there between 6 and 9. So that's how you're going to do it. It's going to get a little bit challenging when you have a curve involved. So let's take a look at this parabola shape. Let's see if we can figure out what the derivative of a parabola or a quadratic would look like. All right, so first of all, you might notice that this parabola starts out with decreasing. And if we draw tangent lines in there, just little baby tangent lines, we can see that those slopes, all those slopes there are negative slopes. And it makes a turn right here. Right there at the bottom is a point where the tangent line would go horizontal. And then from there we see the graph climbing. And so as we draw our tangent lines, now the slopes of those lines are positive. All right, so what is this going to look like in a graph? We want to come down here and we'll just draw a graph right underneath this one. All right, when I draw the graph of the derivative, I like to start with the zeros because they're easy to identify. So this derivative is 0 when x is 1. So I'm going to put a 1 here and mark a 0 point. And if I go before I hit that horizontal tangent line, all of my slopes were negative. In fact, they were negative here, and they get more negative the more we go to the left. So the most negative is up here, and it gets less and less negative in slope as we come towards the 0 of tangent line. So it starts with a big negative number that's getting closer to a 0 value. So in the graph, my derivative is going to start down here and then climb to the 0 value. And I'm not sure exactly what it looks like. Might be a straight line, might be curved. We'll talk more about that in some future lessons. For now, this is good enough. All right, and then as we move forward from the 0, the slopes are positive now, and they're positive and getting more and more steep. So that means the slope or the derivative is positive and climbing. Something like this. All right, so that's the graph of the derivative. We would say here that if this is y equals f of x, the y values in this graph represent f prime of x. And so there's a little summary here of things that you should notice, and this can help as you're graphing derivatives. If your function is increasing, which we saw on the right half of our parabola here, if the function is increasing, then the derivative or the slopes are positive. So f prime would be positive there. And the opposite is true if your function's decreasing, like it is on this left half of the graph. If the function's decreasing, you're going to have negative derivative values. And then when the function is at a maximum or a minimum value, like the turning point right here in an open interval, that point is a place where your derivative will be 0 because your tangent line is horizontal. So if you have a horizontal tangent, then the derivative is 0. Now the derivative also could be undefined, and we will talk, we're actually going to see one in this lesson. The derivative could be undefined at one of those maximum or minimum values, so you have to be careful about that. Okay, so let's see how this works in another example. So in these examples, we're going to want to keep these three things in mind as we graph the derivatives. Okay, now like I said, I like to start by looking for the zeros of the derivative. So the space below here, I'm going to start building my sketch of this derivative. And as I look at this, I can see there are a few horizontal tangent lines. If I was drawing tangent lines, that peak and this peak would be horizontal. And if we were to zoom way in on that one, we would have a horizontal tangent line. So this has 3 horizontal tangent lines, which means in our derivative graph, we're going to have 3 zeros. One right at 0, and the other just before we get to 1 and before we get past -1 over there. So we're going to have one here and here. And I'm not sure why I put that -1 on there. We're going to ignore it. Just these dots, these zeros are important. Okay, where does this graph increase? Because that's where I'm going to plot positive derivative values. So I'm seeing an increase in the beginning of the graph. Way back at -infinity until we hit this 0, our graph is increasing. What does that mean for our derivative? Down here, I'm going to actually make a note. That means our derivative is going to be positive. And there's also an increase happening between these two zeros. We see increasing the slopes. If you draw them in there, you'll see little slight increases even in them. So the derivative is going to be positive where the function f is increasing. Okay. The opposite's true when we see decreasing, and that's this interval. This is a decreasing interval with negative slopes, and another decreasing interval with negative slopes. So our derivative should be negative, and negative to finish the graph. Okay, now look at this little negative slope section as it decreases. Where would you say is the steepest drop in there? Because I'm going to put it right about there. That's the most negative slope. It's right in the middle of that. And in the climb right here, probably right in the middle-ish is the most positive slope with the most steep tangent line. So keeping that in mind, in fact, let's take that example. Between this 0 and this 0 for the derivative, we get peaked out with the slope right there in the middle. So that's going to look like this on the graph. It's going to go positive from one 0 to the other. It's going to peak out somewhere in the middle. And in the negative, it's true in the reverse. Between these two zeros, we're negative, but we're going to peak out or bottom out there in the negatives. Okay, this part's -2, and as x climbs, the slopes get more and more negative. So this negative section is going to keep dropping in the derivative. And coming towards our first 0, we have really positive slopes, big positive numbers that are getting closer to 0. So positive getting closer to 0 in the derivative looks like that. And this is our graph for y equals f prime of x. Okay, so started by looking for the zeros, and there were 3 zeros, which gave us sections or intervals to look at where the derivative is positive, negative, positive, and negative. And those correspond to the function's original behavior of increase, decrease, increase, and decrease. All right, this graph should look familiar. This is our absolute value graph. Now, on this graph, we have a corner. And that corner right there is a place where we're going to see that the derivative does not exist. So the derivative does not exist at corners. which we'll talk about more in a later lesson. But the rest of this graph has some increases and some decreases. So I'm noticing that the beginning of the graph, this whole interval, right till we get to the corner, that the slope is constant. And it's a constant -1 as it's dropping 1 unit for every 1 unit over. And then here on the right half of our absolute value graph, since that's a line, the slope is constant again, this time being a +1. All right, so let's see what that means for our derivative graph. If our slope is constant, our derivative is the same thing as slope. So f prime equals slope. So if I'm going to draw it here, I'm going to draw a constant -1 all the way up until I hit 0 with the open circle, because remember the derivative does not exist at 0 at the corner. And then on the right half, we're on this part of our graph where the slope or the derivative is a constant 1. So 1 constant. The slope is always 1, and so I draw a constant. And here's our graph for y is f prime. Okay, before we look at this one, I really want to encourage you to stop the video and try to describe it, or at least in words, describe what's happening to the slope of this graph in your own words. Come back when you got it. Okay, I'm back too. And the things I'm thinking about this slope are, I don't actually want to write them out. So on this one, the derivative, or the slope, if we look for zeros, do we ever find any? Does this ever go horizontal tangent? It's kind of close at the beginning, and it's getting there at the end, but it's not actually horizontal yet. There's still a slight climb. I say this thing is climbing, so it's not really 0 anywhere. In fact, it's climbing everywhere. So all of the derivative should be positive, since every tangent line I draw has a positive slope. Okay, so the derivative is always positive. Close to 0 at the ends. In other words, the further out we go. And where is it, if it's always positive, where is the most positive slope? I would say it's probably about right here. Most positive slope. And I say that because as it starts curving back down, those slopes get less and less steep. So we've got to draw a graph that kind of does that. All right, so we want to start 0 close to 0 on the ends. Peak out with our slope right past 3, so maybe like 4. We're going to be peaking out, and then we're going to go back to 0 on the ends. So think about what that would look like. Give that a try before you watch mine. Okay, so I'm going to say I'm starting close to 0. I'm going to climb, but then I'm going to peak out and start to drop and get closer again to 0 as I move out towards the end. All right. This is a curve called a logistical curve that you may study in your biology classes. Anybody that's going to major in a biology or science kind of realm, this will be a really familiar graph to you soon if it's not already. Something you guys will learn well. And calculus really helps describe that behavior. All right, let me label this and then we will move on. So I didn't see a name. Oh, this was P. P was a function of the number of yeast cells, it looks like. I don't know. We'll just call it P prime. Okay, finally, I want to use this graph as a test to see if you know what its derivative would be. So this is a graph of y equals 1 over x. You guys know this graph well. It's one of our parent functions. Let's take a look at what the derivative would look like. So start asking yourself this. Is there anywhere where the derivative is 0? Where the slope is 0? Or tangent lines would be horizontal. And I would say here near the end, they get more and more horizontal as the graph drops towards that horizontal asymptote. So near the ends, we want to be, at the ends, we want to be nearing 0. Does the graph increase or decrease or some mixture of both? Now I'm seeing this is a decreasing graph. Tangent lines have negative slope. They're not very negative at the beginning. They get pretty negative right here. More negative, more negative, more negative, more negative. So negative and getting more negative as we get nearer to 0. In this branch of the graph, they're still negative, but and they're pretty deep negative, and then they're getting less and less negative as they get closer to 0 here. So is it fair to say that the derivative is always negative? Close to 0 on the ends? And as x heads to 0, really, really negative. Infinitely negative? They get to more and more vertical directions. Okay, so again, I think you ought to give that a try. Can you draw that graph that fits that description? Always negative. Close to 0, the further we go on the ends, that's an asymptote, people, and gets more and more negative the closer to 0 you get, like this. On the other side of 0, it's very negative and getting closer to 0 as we move out. Okay, question then, do you recognize this function? Because it's the derivative of 1 over x. So you can avoid some baby fraction work maybe if you just have this one memorized. Is it 1 over x squared? Nope. Negative, because we got to reflect it. It's the volcano graph upside down, 1 over x squared. All right, you need to practice these. These take some brain thinking. Have fun with them.